In this section, we talk about some fundamentals about Laplace transformation and transformation in general to understand the basic concept. Now, to understand Laplace transformation, let's talk about what's transformation in general. And to understand that, we need to take a look at what is a weighted integral, because all this integral transformation are nothing but some sort of weighted integral. Now, if you look at this one example of weighted integral here, say for monthly payment of mortgage, so you have plot mortgage against month. The area under the curve will give you how much is the total amount paid over this entire time period. Okay, when this represent the monthly payment, suppose this is m bar, so after time m, say t, you get a total amount paid to be mt bar. Okay, now if we are considering about mortgage payment, think about the bank has already paid the amount and you are trying to pay the loan back. So if you consider the amount paid today should not be considered the same way as the amount paid 10 years later. So definitely the one installment you pay today should have more weightage compared to the amount you'll be paying 10 years later. Now to include that, let's take a look at if you were paying m bar amount per month, and this is done, the weighting is done by suppose an integral weighting factor, which is for our case suppose e to the power negative beta t, where beta is a positive number, so e to the power exponential negative beta t will give you some sort of like exponential decay. Okay, now if you look at the term m bar times e to the power negative beta t, you multiply these two, you'll end up getting another curve like this one. So which represent in this equation this term over here. Now if you take the integral between term 0 and capital T, you get this function, which is your amount paid over the term capital T. Okay, now this function now represent how much was paid over the term capital T. Now you see that now the total payment is now has come to be a function of beta. So now P equals P beta. Now you can analyze the function to understand how much you should make payment like over month, or if you pay for a certain period how much will be paid, or if the beta rate, the decaying rate changes, consider that to be a function of the interest rate. If that changes, how much will be paid down the road, meaning that you can analyze beta in terms of, you can analyze the payment now in terms of another variable, which is the beta. So you have transferred the time domain function into a so-called, what is called this, in the beta domain. So that's through integration what you have done in this case. So that's really the basic of integral transformation in general. Now let's take a look at one of the famous one, which is called this Fourier transform. Now Fourier transform is nothing but an integral transform where the weighting factor is exponential negative I, this imaginary number, square root of negative 1 omega t. So the Fourier transform of a function ft is nothing but the integral over the entire horizon, meaning negative infinity to positive infinity, and the weighting function here is exponential negative I omega t. Now what is this term e to the power negative I omega t? Is nothing but cosine omega t minus I sine omega t. Now let's take a look at it from the perspective of weighted integral. So the Fourier transform of ft is simply the integrated over the entire horizon negative, and you have the function weighted by cosine omega t and then I sine omega t. Okay, that's the weighting factor here. Now if you look at the function again, see that if my original function is a cosine function, cosine alpha t, its Fourier transform is nothing but two terms here. Now I have separated these two terms, the real and imaginary part. The first part is simply cosine alpha t times cosine omega t dt, integrate over the entire horizon, and then the next part is the cosine alpha t times sine omega t, again integrate over the entire horizon. Now let's take a look at what are the values for this integral. Now you know the cosine or sine function, these are symmetric. So if you take the integral over the entire horizon, meaning the negative infinity to positive infinity, you end up getting an area to be 0, meaning that for this case, so this is a negative area, this is a positive area, this is a negative area, and this is positive area, and they go on from negative infinity to positive infinity. All this term will cancel out, meaning that the integral over cosine alpha t dt over the entire horizon infinity to infinity becomes 0. Okay. So now let's look at what are this term, what are the values for this term when you do, instead of taking a regular integral, you take a weighted integral. Now take a look at this first term now. So if you have a cosine function, this is cosine alpha t, and you are multiplying by another function cosine omega t. Now let's take a look at what are these two functions when multiplied means. So I have chosen this to be some sort of harmonics for this case. It can be shown for non-harmonic, meaning that when the frequencies are not integer multiple. Okay, so for this you can see that up to this point we have a positive weighting, so that's correspond to some point over here that gives some positive area, and then after this point you have a negative weighting that's correspond to some part here, so that gives some negative area. Again we have some positive weighting but with some negative value of the function still here, that gives some positive and then some negative, and then again this thing repeats for the entire horizon. And if you take a look for the entire horizon, you'll end up getting a function which is also symmetric around the y-axis, meaning that these positive and negative areas will be cancelled out. Now that's true when omega is not equal alpha. Okay, now let's take a look at what happens when omega equals alpha. So for this case you can see that the function value cosine omega t times cosine alpha t, if you take the integral over the entire horizon, it becomes 0 when omega is not equals alpha. Okay, now what happens when omega equals then alpha? Now for this case you can see here we have this cosine omega alpha t cosine omega t, you have these values to be positive, positive, negative, negative, positive, positive, negative, negative, meaning that when the function is positive, the weighting function is also positive. When the function is negative, the weighting function is also negative. In that case, what's happening? That all these terms are becoming positive, meaning the function is always above the y-axis, meaning that all the area terms are positive. Now, if we take the entire horizon negative infinity to positive infinity, that becomes adds to infinity. Okay, so that's the case when omega equals alpha. So this function cosine alpha t times cosine omega t dt integrated over the entire horizon gives a value of infinity when omega equals alpha, and it gives a value of 0 when omega not equal alpha. Okay, now what about the other term? In the same way we can show that the second term, this imaginary term, really is 0 for all values of omega, meaning that if omega equals alpha and omega not equals alpha, for all values of omega, this term will be 0. Okay, now if we add these two, what we have now, if we look at this function, the transfer function is now not in the time domain, it's in the omega domain, meaning the frequency of the weighting function. So it's in the frequency domain. And what are the values that you have for omega equals alpha? The first part gives infinity, the other part is 0 always. So for omega equals alpha, the function value is infinity. For all other cases, it's 0. Okay, so first of all, it's a transformation because now the function is in the omega domain or the frequency domain. Now if you plot the omega function, so if you plot omega against the function of omega, which is the transfer function, you see that for omega equals alpha, you will get a peak. Okay, now you see that this omega, see that here when omega equals this function is symmetric, so when omega equals negative alpha, that will also get a peak there, because in that case the value is also infinity. Now what does the negative frequency means? All other things we are not going to discuss in details, so we'll only consider that, okay, what our case we consider that, okay, this function is symmetric around the y axis. Okay, now what does it really mean then? So we're saying here, if we have a function alpha t, if you take its Fourier transformation, the transformation can identify the frequency content of the signal. Okay, again, the transformation can identify the frequency content of the signal. Okay, now what are the limitations of this Fourier transform? It's applicable for periodic signals, meaning the signals it can capture the frequency, meaning that the function has to have a frequency. Okay, so it should be a periodic signal. So it's not useful for signals which are not periodic. Consider that an exponential signal. Okay, now control signals are often a combination of periodic and exponential signal. So that's the limitation of Fourier integral, that you cannot really use it for many control signals. Okay, now we can take a look at the approach for exponential signal when there is a suppose exponentially decaying or exponentially growing function. Now if you look at this exponential function e negative alpha t, if you take an integral by using a weighting function e to the power negative beta t, the integral leads to 1 over beta plus alpha. Okay, and this function 1 over beta plus alpha, if you take beta equals negative alpha, this value is infinity. Okay, now you see that we have used that limit here 0 to infinity, because for most control signal we consider at before time value the function is at steady state condition, or the signal or the variable is at a steady state, and that's in the divisional form we'll consider that to be 0. Okay, so typically we consider from 0 to infinite time for in many control applications. Okay, so that becomes beta, for beta equals negative alpha, this will give a value of infinity. Okay, meaning that if you plot this function, this transfer function against beta at negative alpha, so if you plot this, so beta versus this new transformed function, okay, at beta equals negative alpha, whatever the value, you get a peak. Okay, meaning that this exponential weighting can identify the decaying factor in the original signal. Okay, so we have seen that Fourier transform can identify the frequency content of the periodic signal. We see that if you weight it by an integrally decaying term, it can identify the decaying factor in the original signal. Okay, now look at this control signals. Okay, so in many applications we will see some sort of variation like this one. So the length of a spring, you put a mass on the spring and then release it. The length of the spring initially longer and then get shorter, and at certain time it becomes steady at some value. So this function, this type of behavior can be represented by a combination of periodic and exponential function. So if you multiply a sinusoid by an exponential function, you end up getting something like this function. Now for this type of function, what type of transformation can be used? So for periodic signals having an exponential component, if you combine these two transformations, we can identify the frequency content, also identify the decaying factor for this type of signals, and that's exactly what is the Laplace transform. Okay, So if we look at Laplace transform, the definition of Laplace transformation of function is nothing but the integration of a function over 0 to infinity weighted by e to the power negative beta t and e to the power negative I omega t. Combined together, it's e to the power negative st, where s is that complex number beta plus I omega. So what's the benefit? We'll see that it can identify the exponential component and the periodic component. Now also see that if beta equals 0, it simply becomes the Fourier transformation, meaning the Laplace transformation is a more general form of the Fourier transformation. Now take a look at this Laplace transform of some signals. Now if we look at this Laplace transform of this signal e to the power negative twice t and sine 3t, we have this 3 over s plus 2 squared plus 3 squared. That's the Laplace transformation of this function. Now here you can directly from the function you can see this value 3 here and this value 2 here. So we see that from the transformed function itself we can get about the content of the signal, meaning if we go into details, if we take the solution of this or the roots of this polynomial, you see the root will be negative 2 plus minus I3. As you said that this corresponds to beta, this corresponds to the omega. Now we see that there is a exponential component having this decay factor 2 and there is a sinusoidal component having this frequency 3. So from the transformed function we can get those information. Another important property of this Laplace transform is that the Laplace transformation of this derivative can be expressed as a function of the Laplace transform of the original signal itself. What it allows is that you can really express the differential equation in the form of an algebraic equation. That's one of the important characteristics that we'll be using. Okay. Now what are the uses of this Laplace transformation? So you see that in the time domain the model is expressed as this way. In the Laplace domain you see that it expressed in this way. So you see that the signals are separated from another function and that allows representation of the model in the Laplace domain in a simplified form. We can use the block diagram representation where the signals are separated from this function in between which represents the process itself, and we can use the block diagram in a simplified way compared to if I would like to express using the differential equation model. Okay. The other thing is that when you have this different elements in a loop, it can have a differential equation model. If you want to analyze those in the time domain using a set of differential equation, that becomes much more complicated. On the other hand, in the Laplace domain we see that each signals are related by a function, and we'll see later that when you have this you can represent using simple block diagram, and further analysis and manipulation of this equation becomes much more easier because these are in the form of algebraic equation. That makes this manipulation much more easier. Okay, so in a nutshell what we have here that this Laplace transformation allows algebraic manipulation of control signals and the model equations. Also it can identify the signal content. Those two characteristics are very useful for control applications.